Hello, good morning. Very welcome to this webinar that we are sharing with you today. My name is Cornell Roberts and I work for Y.I.C Technologies. And I just wanted to thank Jason from Absolute EMC to invite us to share with you this webinar today. And today we're going to talk to you all about EMC, EMI pre-compliance testing and different solutions that you can use for that. So the topics that we're going to cover is I'll just give you a brief introduction into our company, Y.I.C Technologies. We'll go through the technology on near-field scanning and what the benefits of that can be and how we operate in the near field rather than the far field. We'll show you different solutions that there is available for pre-compliance near-field testing, and also we'll show you different solutions that we have, which we will show you in the live demonstrations today that you can use to mitigate the EMC challenges that you might face. So these are the challenges that we will discuss with you. We will look at decoupling, we will look at current loops, we would look at return paths, ground slots, fences. There's loads of different challenges that you might come across when you do EMC, EMI pre-compliance testing. We just picked a few today that we can discuss with you. And then in the live demo, we will use an RFID board, which is designed by our technical advisor, Professor Arturo Mediano. And with a live demonstration, we will show you certain challenges like these that I've mentioned that you might face. And then you can see how the solutions will help you solve those problems. So just a little bit about our company, Y.I.C Technologies. So we are very proud to say that we are a leading developer in the high resolution, high speed scanning testing solutions. So we've come up with a technology that we have a scanner where we will do real-time scanning in the near field. So we will help engineers, we help designers, we help companies with products that are already complete for fault diagnostics. And our aim is to ensure that the EMC certification happens first time and it's a smooth process for everybody. So a little bit where we are, we've got our main office in the UK. This is where I am based. So this is where all the sales, the marketing, and all the software development is taking place. We also have an office in Canada, in Calgary. This is where we manufacture and do all the hardware development of the solutions that we will show you later on. So we don't have a direct sales network. So we work very closely with our partner network, of which Absolute EMC is our partner in the US, and hence the reason why Jason invited us to do this webinar with you today. So we have two product lines in our company. So we focus on the EMC product line, and this is the near field testing, and it's a tabletop diagnostics tool. And then we have another product line which we focus on antennas. So it's an antenna characterization and measurement tool. And with this specific solution, we can actually measure in the far field. But as we go along the webinar today, all of that will become much clearer to you. So why are we in the business of EMC, EMI pre-compliance testing? Is we want to save our customers the time and the money and obviously the chamber costs. We know that chamber cost is very high, and every time you have to take your product to the chamber to go and have it certified and it doesn't pass, well, then you have to go and repeat the whole process again. So with the solutions that we offer, it's real time and you can do your EMI, EMC debugging in your lab. And it will give you the opportunity to change and retest and make your product ready for that EMC certification. So we design the products, we manufacture the products, and we offer it to our customers so that they can then take their products to market much faster and at a lower cost. So I'm going to, at this point, introduce you to Yoram Shimoni. Yoram will be taking on the rest of the webinar. He's the technical lead for the EMI EMC product range, and he will talk to you about the technology behind the solutions. So Yoram, welcome to the webinar, and thank you very much for joining.
Thank you, Cornell. So give me a minute to share my slides here. Okay. Okay, so thank you so much, Cornell, and thank you all for joining. Let's start. So in this section, I'll talk about why the company. Let's go. We'll talk about the technology behind our product. So essentially, there are really familiar tools to make the EMC pre-compliance testing. We're all using them for a long time. So it's usually either the chamber itself, the antenna, a set of near field probes, or what we are actually our main product, which is the array of antennas. There are advantages and disadvantages for every product, but the key idea is to have a pre-compliance test in the near field at your lab before going to a chamber. This is essentially the essence of this presentation and the tools that we are going to discuss. The idea behind that is to arrived ready for the chamber with a very high level of confidence that you will pass. And you can do that in the near field, in the comfort of the lab, rather than in a chamber environment with the limited equipment that you brought or with the limited equipment that they have. So that's essentially the whole idea. Here we will focus on several tools and several methodologies for testing in this presentation. Okay, hi again. So here we will focus on near field probing or testing. And again, we are operating in the very near field. There is a definition and there is some kind of a structure for the near field. So obviously with the distance based on the wavelength, we are operating in around few millimeters usually from the source, and that's considered to be the reactive region. So there is a coupling effect between the probe itself to the antenna, or the DUT itself. For the EMC, EMI, that's okay. I mean, that allows us to pinpoint sources of emission in essentially high level of resolution. For antenna, it's a bit less comfortable, and you can see from on the left side here, there's a picture of a far field prediction. So one of the key questions that we're getting is can you give us, based on the near field results, can you give us pass-fail prediction? The answer is a bit more complex, and I have a slide that explain that. But focusing on the EMC side of the business, we are actually not giving a prediction, a pass-fail prediction. We will show you the emission sources on your board, their location, frequencies. And the idea behind that is if you see something like that, just fix it. Remove the risk of failed and many more risks, but eliminate that source and probably increase your chances to pass the test, and of course improve the design of the product itself. Okay, so a bit of advantages or benefits of near field scanning. So obviously, compliance and troubleshooting, very easy to do it in your lab environment. Signal integrity, it's a non-destructive test, optimization, component level analysis. All these things essentially you cannot do with a single antenna 3 meters or 10 meters away. You will get a fairly good description of the emission from your board, but it will be very difficult to pinpoint the specific location of a source or to understand the behavior of a certain circuit. And we will see that further down the line. So obviously, early detection of the hotspot will help you guys to mitigate that and obviously save time and money on the chambers. The signal integrity or actually the quality of the design, especially in the digital age, you would like some application really monitoring the bear, for example. So we'd like to control that. All kind of other uh, problems may occur, crosstalk, noise that being distributed across the board to an area which is shouldn't be. And again, I'll show you some pictures of that. Um, and again, simplicity of testing. You don't need to take anything apart. We have a lot of customer that they just put their products on a scanner, essentially the complete product. They don't need to do any adjustment. Just run scans in a few seconds. They can get some kind of an indication, an overview of the emission coming from their product. Optimization, again, you will see what's going on in the product. It will, or in the DOT, it will help you to optimize the design either to your needs or to exceed essentially expectation, especially around complex PCB, high density PCB. It's become more and more and more complex. Last thing is actually component level analysis, and this is the key advantage of working on high resolution near field. It allows the user to zoom in into a specific area. Sometimes it can be really, really small, especially today's with a really small component, 0.2, 0.4. And if we're talking about silicons, we're talking here about micrometers. So obviously you can do that when you're further away from the DUT. You need a tool with the ability to scan in a very high resolution, the DUT and in high proximity. Next, the methods of operations. So usually the first thing that the user will do, and let me turn on my pointer here to help me a bit. So usually the first thing that the user will do is a quick frequency sweep. Essentially, you would like to see which frequencies are available or are emitted from your device, their magnitude, the range. That will give a pretty good description or understanding of what's going on the DUT. Next, you would like to mitigate based on priority, of course, the higher level of emission, you would like to reduce or remove that or to mitigate the source or this level of emission. You will probably select a certain frequency, and the next thing will be to run a special scan. Uh, that will give you the location of this specific frequency, how it's being distributed across the board, and where it's being generated and emitted from. And here you can see quite clearly that certain frequencies concentrated in a specific area. The next is how to solve that. And again, that depends on the design, either with a shield or changing the coupling network, ferrite, or whatever other tools that available at your disposals. But at least now you know which frequency is problematic and where it's being emitted from. The rest is to mitigate that problem. The next thing is actually a combination of a sweep spectral and spatial scan. And the idea here, usually the user will do that at the end once he remove or eliminate most of the issues. That will collect a lot of information. In our tools, usually this scan is the slowest, but that will allow the user to collect wide range of information, actually across the frequency range in a very high resolution, and you can save this information your database for future use. Uh, and again, for records, just to make sure that you did release this DOT as expected. Another very important point is interleaved scan. As we know, a magnetic field is actually a vector, it has a direction, and the orientation of the magnetic probe is really, really important. Here you can see an example that a certain trace is aligned essentially with the probe, and that prevents us from getting a clear picture of the trace. However, turning on interleaved mode will allow to scan or measure the magnetic field in every point in both orientation. And then the software essentially will combine them. Now, that will give a fairly complete description of the trace and the emission coming from the trace. It's a bit more difficult to do it by hand, but again, skilled engineer can understand that something is there. The problem with fact essentially that magnetic field is a vector is that sometimes an unexperienced engineer will use typically a single probe. They will put the probe on a certain location and then suddenly they don't see anything. So it's important to actually make two measurements 90 degrees apart that can completely change the picture. So interleaved scan, pay attention to the orientation of the probe, uh, very important, and that essentially provide a more complete picture of the emission from the DUT. Another another problem or issue that you will need some kind of an automation. Usually, it's some problems that it's an intermittent problem. It's coming and going. There's no real way to synchronize to that problem. And sometimes with a spectrum analyzer, usually it's very, very, very difficult to capture. So for this, you will need some kind of an automation to capture this event. And the idea behind that is just a peak hold and continuous run. So once you have some kind of a software to automate that process, you can just run the scans over and over and over and over again while preserving the measured data or the peaks. And essentially, with time, statistically, you will capture something, at least some kind of an indication. But intermittent events is very, very challenging, specifically if you don't have any other means to capture or to trigger on them. You don't know the exact level. The pulse is too short to trigger either the scope or the oscilloscope or the spectrum analyzer. So it's sometimes it's a real issue. You do see that in the behavior of the DUT, but it's very, very difficult to capture and understand where they are coming from. And from our experience, the best way to do that is just to have a software, an automated software that can support peak hold and continuous run. And eventually you leave it running for a minute, 5 minutes, half an hour. Eventually you will capture that event. Next, immunity insights. So EMI is again very important part of our testing, not just for compliance purposes, but also for the functionality of the DUT. Near field immunity insight allows you to transmit specific frequencies at a specific level to a specific area of the DUT. That will allow you to test the functionality of your DUT once you are emitting radiation to a very specific location. And of course, you can characterize the level, the absorption levels, and the transmit levels. So most of the probes are bidirectional. course, depends if there is any kind of hardware behind them, but at least ours are bidirectional. You can, instead of a spectrum analyzer, you can use a VNA or just a signal source, and you can set the area. Yes, you can see here, you can set the area and the time and the frequency of transmission, and we will start to transmit to a very specific location. Obviously, you will need another layer of software to monitor the functionality of the device, monitor errors and things like that. But with our tools, you can set the transmission and the EMI setting side from our software. The functionality, of course, it's out of our reach. Uh, Far field prediction. So I mentioned that briefly. So we have the RF scanner. With the RF scanner, as you can see here, you can just place the antenna, you click run, and you get anything that you want to know about the antenna, the gain, efficiency, TRP, and far field prediction. So this is how it looks like. It's very similar to a chamber results, not 100%, but it gives really good indications how the antenna will behave. And there are, again, two common methods. We're using both of them to predict the far field based on near field results or measurements. So if we can do that and we have the technology to do that, why can't we just give the EMC guys pass fail? This is something that people are always asking. Uh, and the answer is actually very simple. It's phase thing. With antenna is a device that designs to emit. It has a coherent behavior. We can monitor the phase progress of that antenna, and we see some kind of a predictable behavior. PCB is a mess, specifically complex PCBs with many different frequencies, sometimes, very noisy environment. There's no way to get something like, where's the mouse, something like that. This is essentially the phase distribution of the measured antenna. There's no way for us to get that clear in a clear way from a PCB. And this is a critical thing that we need in order to calculate and predict the far field. So we are looking into that and we are trying to do that. But the ability or our ability to predict a pass fail in EMC depends on the complexity of the PCB. Usually with simple PCB, it will be easier to do, but with the level of complexity that we have today, so far we couldn't do that. Um, so the idea is to show you guys the emission, the level of emission that we measure, and again that depends on the PCB itself, the structure, ground layers, and then allow the user to mitigate that specific location, frequency, emission, and by that to increase the potential to essentially to pass the test and improve the product before going to the chamber. But to predict success with complex PCB is very difficult mathematically. At least for now, we're still trying to find an elegant solution. Okay, so we have here a live demo, and I'm using several uh, products. So let's review the solutions a bit before we will move to the live product, a live demo. So in general, there are two kinds of solutions when you're talking about near field measurements. It's either a scanner, which essentially an array of antennas, or a single probe solution. So here you can see our scanners. It's the EM scanner family or the EMS family. Uh, we have this scanner, which is the EMS, and we have this one, which is the R version, stands for high resolution. For this scanner, the EM, the resolution is 7.5 millimeter. That's the physical distance between the antennas. And thought I had a picture here of the boards, maybe in the next slide or so. Um, so we can actually make measurements 7.5 millimeters apart. In the high resolution, uh, we placed that board on a set of XY motors, essentially rails, and we can precisely move that board. So in each 7.5 millimeter cell here, we will kind of divide it to two in each axis, and we can make four measurements. Each will be, that will give us a resolution of half of that 3.75. And we can repeat this process. So every subcell will be divided further into two in each axis. And that's why we can achieve a resolution of 0.06 millimeters. Now, to be honest, for regular PCB, this is way more than enough. Even just a 7.5 millimeters will give you a pretty good indication. I think it's about quarter of an inch, right? Correct me if I'm wrong. Uh, Usually for PCBs, the native resolution is enough. High resolution is mostly being used for high density PCBs or very small products. We had a customer with they developed a earpiece. So the whole size of that was around 8 millimeters. So obviously they can't use the regular scanners. Uh, or if you have a silicon, if you want to map the emission from a chip, from an IC, usually you will need a very high resolution, and 7.5 millimeter will not be enough. But if you're worried about connectors, cables, regular PCBs, definitely the regular scanner is sufficient. 7.5 millimeters will give you a pretty good indication where that source located on the board. And specifically, if you are the engineer who designed that board, you will know exactly what's going on. Typical frequency range of the scanners, it is up to 8 gigahertz. It's way above what you need, but we covered that. And again, the special resolution, the native resolution is 7.5 millimeter all the way to 0.06. The scanning area is something like an A4, a printed page, a printer page. Uh, we do have requests specifically from car manufacturer and people who design really, really big boards, if you can address that. And the answer, yes, but it's getting very expensive for a very big scanners. The way that we do that is we can either move the scanner, and that's the cost-effective solution, or we can connect multiple scanners together with RF switch, and then the software will stitch everything together. Uh, that will be the best solution from signal integrity, but that's very high. That will introduce very high cost to that solution. If we're talking about multiple probes solution, scanning large area become really, really expensive because of the cost of the essentially of the antenna arrays. That's the reason we added the feature to actually move the scanner around, and then we will stitch the results in software instead of using multiple scanners. Um, the maximum radiated power that we can absorb is around 10 watt or 40 dBm. This is what the power that we can handle internally within the design. And these tables shows you a bit of time estimation, how long it takes to scan. Um, Time, of course, is often of the essence. The scanner is much faster than a single probe solution, but still we do have limitations, specifically when you're looking into high resolution. It takes time. We need to trigger the spectrum analyzer. We need to pull the results, the measurements from the spectrum analyzer. And if it's high resolution, we need to move the scanner a bit. So this process takes time, uh, but it's still much, much, much faster than a single probe solution. Here you can see the difference between 7.5 millimeter scan to sub-millimeter scan. So again, for most of the engineers or DUT, 7.5 millimeter might be enough. But the high resolution one, you can start seeing structures within the IC. Again, there's no good and bad here. It's more suitable based on your needs, essentially, if you do need the high resolution or not. Next we can speak about the single probe solution. With the single probe solution, actually the trade-off here is time. It's still a moving elements. You place the probe in a certain location, trigger the spectrum analyzer, take the measurements. It's a bit more flexible than a scanner, due to the ability to change probes. And at least from our probes, you can see the probes, our probes down here. And I don't know if it's visible, but we have some kind of a 3D adapter here that we share the design so you can 3D print adapter for any probe that you want. So essentially, this approach is much more flexible than the scanners. However, you pay with time. The advantages are the cost. Usually, single probe solution will be a more cost-effective solution. And the z-axis, the ability to go above certain obstacle or to really get close to a certain location. Obviously, with this approach, you scan the top side, and with the scanner, we scan the bottom side of the PCB. But again, depends which DUT are you scanning, if you can actually flip it over or not. But keep in mind that a ground layer in the middle of the PCB will shield emission from the antennas. So we will not see that if there is some kind of a ground layer. So advantages and disadvantages, again, there's no good and bad. It's more like what is suitable for you guys, for the user itself. So here you can see a robotic arm. And again, everything is being controlled by the software. So you can define a certain area to scan, and you can choose the probe. You can choose the size of the robotic arm. Here it's just a robotic arm. What I have here is also 1 meter. Actually, it looks like a bit more than a meter of a rail, so much bigger DUT. I can handle much bigger DUT. You can see the rail here, one of them here. Again, much more flexible than the scanner. Next one is the handheld. And here you can see a video of the handheld probes. And the advantage with at least the technology of today and the speed of the computers is the ability to connect a camera to all that. Now we added these RGB markers to the probe, so that allows the camera to track the probe movement. We make the measurements and we overlay the measurements on the real-time video stream. So you can see exactly what, where the probe is, and then you can record the measurement. It's not like you're connecting the probe to a spectrum analyzer. Then you need to look into the spectrum analyzer screen. All you need to do is actually wave the probe around, take the measurements, and then all the information will be recorded. You can easily go to the software, turn on the 3D mode, and start manipulate the information. Uh, so again, this is not available with any probe, only with our probes. Essentially, I don't know if it's visible, but we have the RGB markers to track the probe, and we have some kind of a QR code to indicate which probe we are using or the user is using, and then we can automatically compensate for the response of that probe. The reason that we have three colors is because there are PCBs in multiple colors. So we need only to identify two of the tracking circles. And then if it's red DUT, it's enough for us to capture the green and blue, and essentially everything will work. But we found out that, first of all, we couldn't find a single color that will match all. And we found that two colors is not sufficient. To really distinguish the probe from the background with the multiple colors of products and DUTs, we need three colors. So that's the reason we have three colors marker. Another key component is essentially the spectrum analyzers. So we are working with many spectrum analyzer, mostly Enritsu, Keysight, and Rode. These are the top three companies. They're doing great work. No complaints on their spectrum analyzers. Some models are better than the others, but the recommendation is to work with good spectrum analyzer. There are many customers with Regalant. They are very cost effective and good spectrum analyzer. Uh, Again, we didn't see any major issues with them. They're doing the job, but obviously you have the Enritsu, Keysight, and Rode. We also recently started working with Signal Hound with the BB60C. These things are very fast. It's a USB screenless spectrum analyzer, very affordable price, and based on our limited experience, we have a very good results from it, and very fast. Again, terahertz per second. So spectrum analyzer, very important to have a very good and calibrated spectrum analyzer. Okay, uh, let's see some of the measurements, the thing that we captured and show and we can discuss. Next, come on. Okay, so the idea behind all that is essentially in-depth PCB analysis and verification. Of course, also a complete product, but you do want to mitigate the problems on the PCB levels. So we can look into sources, current paths, the distribution of noise across the PCB, coupling between different components of the PCB. All that we can do during the prototyping or essentially pre-production. Again, when you have at least the first version of the product in your lab and you're looking into that. And of course, also for post-production, just to verify that post-production or production units behaving as expected. And you don't want to get the complaints from a customer after distribution that something went wrong. And the boards, the measurements that we will talk about, it's actually taking from our EDU kit. And again, Professor Arturo Mediano designed several circuits to emphasize problems or bad PCB practice. So the first one that we will see is this circuit. So essentially, it's a simple clock circuit, but in this case, we can engage some coupling network. You can see the ferrite and the capacitor here, and we can choose the current return path. One will create a big loop and the other one a small loop. But essentially, it's just a clock IC, just to emphasize how important, in the next slide, you will see how important the return path is. And this is how it looks like. So essentially, just by changing the return path of the current, you can see 10 dB reduction in the emission level without any filtering, any decoupling capacity. And you can see how it looks on the scanner itself. So by changing the jumpers here, we can simply uh, change the return path of the current. And only by doing that, it's a bit difficult to see, but you can achieve an average of about 10 dB reduction in the measured emission. Uh, Another thing is the turning on or engage the filtering, essentially ferrite or or capacitor. So again, here the emission level went down from minus 49 dBm to minus 67. So rank again close to 20 dB reduction. Uh, very important to choose the right component, the right filtering. But the thing is that you can see that visually here, and if the capacitor is not in the right value, you can easily solder another one, change it, and see the impact. And you can compare. You can compare the results with different components. Again, this is just the ferritin gauge. So again, ferret essentially it's high resistance for high frequency. So based on the ferrite values, again, you need to design the right one and to solder the right one. But just by engaging ferrite, we're achieving around 20 dB reduction in the emission levels. And again, it's very visible. And that's the advantage of that. You can actually, so again, this board was designed for students, for universities, so they can easily replace the ferrets and see different behavior. But I think it's very good for us as well, the more experienced guy, to actually see the effect of ferrite in the system in the current path, the value and the impact on the emission. Oh, this one is important. So slots. So this is a common practice. Sometimes you want to separate a board, so you the design introduce a slot in the ground plane just to separate the boards. Well, it's not always working. And the next slide will show one of our board essentially that we suffered that problem. So here you can see that the current is going straight through. The expectation is that it's essentially will go around the slot following essentially the trace. So it's very important to design the gap in the ground slots or in slots in general. Also ventilation is all you will see later on. Specifically high frequency, they're just going straight through. And you can see that here. So essentially, this is our board. This is the board that measured the phase at the RF scanner, one of the first designs. This portion here is the digital portion, and this portion here is the RF portion. So there is a separation on the ground here, and there are also a via fence. But yet we still saw a lot of digital information on the RF side. And then we simply scan the board. And then it's very visible. There is a trace here, or two traces which are very close together. And even with the via fence and the ground separation, we could still see digital information or digital frequencies on the RF side. So we had to redesign that board to mitigate that issue. But at least you know what the problem is. You can see exactly where it's coming from, and now you can find the right solution. Crosstalk leaks, again, very simple example, but I think it's very powerful. Here it's a array of switches. And during this scan, all of them are open, and you can see that there is no current essentially here, very low level of current. So if they're all open, why I have current on the return path here? And so again, you do see current linkage even in switches. Uh, Nothing can stop the emission or the coupling of, especially in a PCB, in dense PCB. So you definitely can see that here. It's very good example, and I think it's very powerful because I think switch is especially mechanical switch. It's a switch. It's either on or off. Well, it's not exactly the case. Shielding. We have a customer that change the handle of a product from just a regular handle to a pop-up handle, and that caused them to fail. So design of a shield and verification of a shield is very important thing. So just when you have a product, you need to scan it or to measure that. product after the final assembly. Uh, Actually, the example that I had in mind is with the antennas. Many customer are buying antennas and they're looking into the specification of the antenna. But once they're placing the antenna in the final product, maybe there is an enclosure or something, piece of metal close by, it's completely changed the behavior of the antenna. Very similar to EMC. If you put your DUT or your card in the enclosure, the behavior might change. Very important to verify that and make sure that the enclosure is doing what it's supposed to do. And that's the example, the ventilation hole examples. Uh, you can see that the current is actually, or emission is going through the ventilation holes. So again, the gaps between ventilations or the size of the ventilation hole is very important. In this example, we solved the problem immediately by changing the power cable location. And the idea is that the board itself will protect it because of the ground layer. So again, you can easily see the difference. Uh, and just emphasize the fact that sometimes the solution is very cheap. It can be even with no cost at all. But you need to know where the problem is coming from, and then you can think about the way to mitigate that. Uh, Kind of a non-EMC related applications. The assumption is that any component radiates within its frequency of operation, especially digital part. So if you see something like that, uh, probably something wrong here. If this is a certain digital IC, clock, VCO, I don't know, something. If you expect to see some kind of emission there, it's very easy to identify. If you don't see anything and you expect to see something, so probably something bad with this IC. So this is example of essentially using EMC equipment for a non-EMC application, and in this case, fault diagnostics. Oh yes, charging, wireless charging. So we are working with car manufacturer, and one of them they're thinking about wireless charging, and they wanted to characterize the emission of the charger beneath the car. And they asked us if we can do that. Um, well, the answer was, I wish we can, but because they were talking about 14 kilowatts of power, which obviously we can't handle. But the home wireless chargers or the ones with lower current and power output, obviously we can measure. And so essentially anything that emits can be measured and characterized by probes. And especially if you have the software that will give you really nice understanding of the behavior of that specific component. And we will see that in the live demo.
Hello, apologies everyone. I think Yoram's just lost his microphone, so we'll just give him a minute to join back in. Sorry about that. Hello, everyone. Apologies for that. Yes, Yoram's internet just dropped out, so he'll be back in 1 minute. Sorry about that, guys.
Thank you.
Hello, everyone. Okay, it looks like he's back, and now he is.
I'm back.
Yes, he's back.
Sorry, I
Oh,
just lost the internet. I don't know.
phew.
When we're in the same office, so I don't know
I
why
know.
I lost it. Okay,
Okay.
share. Okay, back. Um, okay, so the live demo will be in with RFID. Okay, so this is the board that we're going to. You can hear me, right? Everything is okay? Good. Yes. So RFID boards. So again, this is one of our demo boards. Here there's a kind of a small processor running on 32 megahertz here. Then we have another processor here, a very small IC with a 27 megahertz clock, and this is essentially the RFID. This is how the system looks like. I have my laptop here with the software. Here I'm using actually the high resolution, the robotic arm, and I have the handheld kit. I'm using Keysight N9917B, I think, connected to the system. And let me try and show you guys the camera. Okay, so this is the setup that we have. So you can see the board itself on the scanner, and you can see the robotic arm and the rail here. And this is our near field probe connected. So let me share everything now, and we can go to the application. Okay, so see my screen.
Yeah.
So obviously I prepared everything in advance. So uh, this is essentially the scanner itself. I placed the board on the scanner. Here I can select the area of the scan. So we'll scan the digital portion. I would like to understand what's going on in the cable, and then we will select this area as well, which is the antenna. Uh, this is the analyzer setting, 10 to 310. I enabled the preamplifier. So this section will be different per spectrum analyzer, depending on the ability or the functionality of the spectrum analyzer. Here you can select the spectrum analyzer. You can work with multiple spectrum analyzers. Next is just OK and run. Oops. So run and we start scanning. And this is essentially what we see. And let's give it a minute to finish and we can discuss this mountain. As you can see, when we reach here, we can see that frequency coming up, which is 13 megahertz, and this is the RFID frequency. And you can see that it's coming specifically from the antenna area. But this mountain here is very dangerous mountain for us. And this is coming from the DC to DC converter. And you can see that it's coming from here. So now it's done. And we can essentially zoom in, put it in 3D mode, and we can play with that a bit. So obviously this area here is the 13 megahertz of the antenna. You can see the antenna itself. But this thing is a bit of a concern. So here, if we'll choose a specific frequency, we can see that it's coming from that area, the coil and this DC to DC converter mechanism. The problem is not just here. The problem is that you can see that that specific frequency, which is 123, essentially travel across the with the cable, across the cable all the way to the RF section. And that will essentially coupled with the antenna and you will see that over the air. So if the application is kind of a bare sensitive, I don't know what it is, it's less important for RFID, but for video, for example, that will cause problem in the transmission. It will be embedded into the transmission. So this one is very clear and very visible. If we will choose the 13 megahertz, we can see that it's actually pretty good. Some of it is reaching the digital portion, but it's mostly concentrated around the area of the antenna. There are a few frequencies here, like this area here. So this is the 27, and it's coming from here. So this is the processor that I mentioned. And of course, there's another 32. But again, very difficult to see. The next thing that I will do is disconnect the power supply to the board, and let's move to a battery operation, and let's see how that will change the results. So this is a battery. So now it's the same functionality, but powered by battery. I didn't change anything. I'm just rescan everything. So now the scale completely different. So obviously we see the 13 megahertz around here, and we see many little sources of emission here. And let's review these. So all this area is pretty quiet, and this is again the coil DC to DC converter. Okay, so we're done. We can select this area here and see what's going on here. So obviously this is the frequency of the microcontroller clock, the 32 megahertz. And again, you see that very clearly here. So it's been generated here by the VCO going all the way through the communication SPI. So I think it's SPI. And still you can see some of it around here. So it's not that good, but we kind of see some level of it around the antenna, but you can clearly see how that frequency travels across the cable all the way to the other side of the processor of the unit. If we'll go to the 27 megahertz, we will see where the 27 megahertz is coming from, and this is coming from that processor right here. So again, we can see the distribution of a specific frequency. With the 27 megahertz, we can see that it's actually present on the other side as well. even though on this side, on the left side, there's no 27 source at all. Next thing is the sources, the harmonics. So obviously we can see many harmonics here. This one is the 27 harmonics, and this one caused damage around here as well. So higher frequency, and that travels across the cables all the way to the other side. So very visible. And next, again, we can look into the to the robotic arm. So the advantage of the robotic arm is essentially the top side. Now I'm laughing here because Cornell just reminded me to switch the RF cable. We have only one spectrum analyzer. So I'm going to connect the robotic arm, and you can see that I took a measurement of that specific thing. So we're only going to measure this one as I have an overlay of that portion here. So in this area, essentially what we're after is the connector. So we can test that area and see exactly what's going on. Now, in the video, do you see my video? In the video, you can see the movement of everything. So essentially, I'm just selecting an area. Analyzer setting is the same. This is the control level, essentially the resolution of the scan. So now it will be 3.7.5 millimeter. Okay, and run. So I don't know if it's visible in the video, but you can see now that everything is doing its scan. Now, here you can see frequencies which in a bit higher amplitude. It's a different probe, and we're scanning the top side. So we can see exactly what's going on the top side. And again, we can see the 32 megahertz really dominant around that area. Slowly it's built everything. So these are the differences. We can actually compare the two scans based on the area. So if we look into this section here, you can see that in orange. And this is the area that we just scanned. And the last thing is the near field probes. So this is obviously the entry-level solution, but we think that with the camera, with the integration of a video camera and the overlay of the measurements on the live video, this is actually a very powerful tool. So from a setting perspective, sorry. So analyzer sets to exactly the same value. You can turn on the preamplifier. So here we're selecting the live track, and we can reduce the exposure level a bit. And that's it. We can essentially click run. And now it's enough for me to put the probes in view, and we can start making measurements. And this is like real time. So again, a very powerful solution with the integration of a video camera, the software, the overlay of the measurements on the live video stream. So this is how it works. So yeah. So I think this is it from my perspective. I think I shared a lot of information here, and hopefully it was beneficial for you guys. Cornel, I think we can open the floor for a few questions, but just stop sharing.
Brilliant. Thank you very much, Yoram. I think we all learned something new about EMC today. So I would just like the opportunity to hand over to Jason from Absolute EMC. Jason, if you would like to say something at this point.
Sure. Thank you everyone for coming. If you have any questions that come up, now or even after the presentation, we have to answer you. We have, please check out our websites, absolute-emc.com. We have a full line of tools to help um, you with your EMC needs. We have a calculator section and lots of articles. Also, we cover test equipment, from pre-compliant with the Y.I.C technologies products, for development and engineering work. And we have tools that pretty much cover all EMC testing to full compliant testing as well. So if you have kind of needs of or you're having an issue with a product and you want to know what might work best, we try to help you out as best we can and answer your questions and see what might be your best tools to help you out. So I guess we have a hand up here from Jody.
Hey, Jason. Maybe you said it earlier. Will we be getting a slide deck or some type of marketing collateral for this product?
Yes.
Maybe I can answer that. So this webinar has been recorded today, and I will be distributing the webinar to everybody. And then, yes, if you need any more information, just get in touch with Jason or myself, and we will be able to send it to you, and the slides, of course.
And this is for distribution to customers. There's nothing proprietary.
This is a training for customers as it is. This is open for all customers.
Okay.
Okay, do we have any more questions for either Yoram or Jason?
Yoram, would you be able to show a quick demo on the flat scanner of how you can achieve the higher resolution, or does that require a more complex setup?
No, it's actually ready. Let me share everything. Oh, it does require to switch back the RF cable. Let me find that in a minute. Okay, so let me share. So essentially, this is the node of the high resolution. Again, just to save time, I'll scan a specific area, smaller area. And this is the control level. So now you can see here, and actually we can turn on the interleave mode as well. So you can see here that the resolution is 7.5 millimeter. That means it will do one measurement in the middle of every square here. And this is again 2 or 3, so it's 1 point. Let's do level 4, which is just below 1 millimeter. And that's it, essentially just click run. So I don't know if you can hear that, but and now we're operating and you can see how we're making the measurements. So the trade-off is essentially time, because I think it's 2 by the power of 4 measurements that we're doing now in every cell. So you will have to wait a bit.
Right, that makes sense. And you said the way that that's done is that it's moving the board with the array of antennas inside the box, or I'm just
Yes, I'll stop
confused as to how that
sharing.
works.
So you will see that, I don't know if you see my camera now a bit bigger. So if you can see the board, so you can see the scanner actually moving, slightly moving
Oh,
below it. Is it visible?
yes, we can see that.
Yeah, so maybe this camera resolution, but you can see it on the software itself, how we are actually making the measurements right here.
Awesome, thank you. That's good to
You're welcome.
see.
And again, it's exactly the same setup. All you need to do is just adjust essentially the control level here. That will
Okay,
adjust the resolution.
and that's only available with the R model of the scanner?
Yes, yes. The EMS itself is essentially the array of the antenna, and again, it's 7.5 millimeter. And the R version, it's the entire, construction of the rails and everything internally.
Great.
And in the future, we're thinking to add internal spectrum analyzer as well, so it will be a complete enclosed solution.
Awesome. Cool. Thank you.
Great.
Okay, next we have Jody.
Yes. Can you tell me again what the maximum frequency is on each of the products? I don't remember.
8 gigahertz.
Okay.
Well,
Is there
the handheld probes are more around 14 gigahertz.
okay? Is there anything on the roadmap? I worked with y'all when you were in a previous life, and as I recalled, I thought there was something on the roadmap to try to get to 20 gigahertz, or is that am I imagining something?
No, it's still on the roadmap.
Okay.
Yes, I mean we made a lot of improvement and changes since MScan's days. We had to rewrite a lot of the firmware and the software once we took over. We are working on the 20 gigahertz. We have the design, but and hopefully we will do it in the next year. But we need to clear the table, make sure that we have, two solid product lines before moving forward. So we're almost there. We're definitely thinking about that. We have kind of the design. We don't have prototype yet. But the priority at the moment is to improve few things that we have on our table and then to move to the next one.
Okay. Again, this is 5 years ago, I think, and I just remember when we ran around my territory, we got a lot of interest from a lot of my customers, but the 8 gigahertz frequency limit was a problem. They all were looking for something KU, K band, that type of stuff.
Yeah, for the antennas.
Yeah, correct.
Yeah. So we do have that. There was, so when we took over from MScan, there was some legal implication of what Apple is taking and what we can have. So it took a while for us to get our act together. With the EM, it was much simpler, but especially with the RF, they wanted some of the technology. So we're almost there. We're still looking into it. We will have a solution, but I cannot commit at that point on timescale.
Okay. No problem. Thank you.
Yeah, that's a good question. It's a painful question, I would say. It's a painful question.
All right, brilliant. Thank you very much, Yoram. And for all your questions. I'm going to end the webinar here, I think. On the slide that you can see, there's all the details of Yoram, myself, and Jason. If you need any further information on this webinar or the products or solutions, please get in touch. We would love to hear from you. Thank you for attending today. I will definitely send out the recording and the slide deck, and I really hope to speak to you really soon. Thank you very much for your time and have a wonderful rest of the day. Thank you, guys. Bye.
Thank you. Bye-bye.
Bye.